Friends, in the last lesson, data transfer and arithmetic instructions were introduced. Now this lesson introduces logic and branch instructions. Logic instructions are needed for execution of an instruction. The contents of program counter are sent out to memory to fetch the operation code. The program counter increments automatically. The operation code is copied onto instruction register and is decoded, and then the execution of instruction starts. Now let us discuss the logic instructions. The function of the logic gates like AND, OR, NOT, exclusive OR, etc. can be realized in a microprocessor with the help of logic instructions. Let us take these logic instructions one by one. In AND instruction, the contents of accumulator are ANDed bit by bit with the data byte. The result is stored in the accumulator. In AND instruction, one of the operand is always available in accumulator. All the flags, they are affected by this instruction. Carry and auxiliary carry flags, they are not affected, as auxiliary carry flag is set and carry flag is reset. There are three variations of AND instructions depending upon the availability of the second operand, that is based on addressing modes. These are ANI data, that's ANDing the content of accumulator with a data byte, and the result is stored in accumulator. Next variation is ANAR, that's ANDing accumulator contents with the contents of one of the register, and the result is stored in accumulator. Then we have ANAM, that's ANDing the content of accumulator with a memory data whose address is indirectly pointed out by HL register pair. Now the first instruction, ANI data, is immediate addressed. The second one is the register addressing. The third one involves the register indirect addressing. These three variations of AND instructions can be explained from the following diagrams. In ANI data, one of the operand XX is in accumulator, and the second operand YY is in memory. The result of ANDing XX and YY is stored back in accumulator. It's a 2-byte instruction. So after fetching this instruction, the contents of program counter is incremented by 2. In ANAR, the contents XX of accumulator are ANDed with the contents YY of one of the registers, and the result is stored back in accumulator. In ANAM, the contents XX of accumulator are ANDed with the memory data YY, whose address PPQQ is indirectly pointed out by HL register pair. The result is stored back in accumulator. We take an example of AND instruction. Let the content of A is C, C, H, and the content of B is F1, H. On execution of ANAB instruction, it results in A is equal to C0, that's 1100, 0000. Now the status of the various flags is sign flag is set, Z flag is not set, parity flag is set, and the carry flag is not set because of the architecture of 885, and the auxiliary carry is set. Let's discuss the applications of AND instructions. AND instructions are used for masking and bits resetting. Let's study them through example. First we discuss about masking. Now let the content of A be described by A0 to A7. On execution of ANI 01 instruction results in A is equal to 0000 A0. That's except A0, all the bits of the accumulator have become 0. That is, in other terms, we have masked by selecting ANI 01 instruction the bits from A1 to A7. Now, if A0 is 0, Z flag is set, and if A0 is 1, Z flag is not set. Now, let us discuss the other applications of AND instruction, that is bit resetting. Now, let the content of A is 1100, 1100, and let's say A3 bit of this accumulator needs to be reset. This is possible by selecting a control word as F7, that is ending with F7, that is 0, 1, 1, 1. So that is what we do. We do ending immediate with F7, and the result of this ending is 1100, 0, 1, 0, 0. Now in this case, the bit A3 is reset. Any of these bits of the accumulator or the bits can be reset by using ANI instruction and choosing the appropriate control word for it. We now take on the next logic instruction, that is the OR instruction. In OR instruction, the contents of accumulator are OR bit by bit with the data byte, and the result is stored back in accumulator. OR instructions affects all the flags except the carry and the auxiliary carry, which are reset by this OR instruction. Like AND instruction, OR instructions are also of three types, that is ORI data, ORAR, and ORAM. Now let's discuss them through an example. Let the content of A and B are as given. On execution of ORAB instruction results in A being 1111, 1101, that is 0, 1 is OR, that gives 1, and 0, 0 gives 0. In this way we obtain this. The status of the various flag is sign flag is set, 0 flag is 0, and parity is 0. Now we discuss the application of OR instruction, that is it's used for bit setting. Let's say that this particular bit we want to set, that is A4. Now for this thing we select an instruction ORI 10H. Now this results in the content of accumulator being 1101 and then 1100. So this bit is set by executing this instruction. Now we take on the exclusive OR instruction. In exclusive OR instruction, the content of accumulator are exclusive ORed bit by bit with the data byte, and the result is stored back in accumulator. This instruction affects all the flags except the carry and the auxiliary carry. Now, exclusive OR instructions are also of three kinds, that is exclusive OR immediate, XRI data, XRA R, and XRA M. Let's take an example of exclusive OR instruction. Let the content of A and B are as given. On execution of XRAB instruction, the contents of A becomes 0011, 1101. That is, if the two bits they are same, the exclusive OR gives 0, and if the two bits they are different, the exclusive OR gate gives 1. So on that basis we have 0 1, that's 1, 0 0 gives us 0, and in this way we get the content of A. The status of various flags is sign flag is 0, Z flag is 0, and parity is 0. Let's now discuss compare instruction. The function of a comparator can be realized in a microprocessor with the help of compare instructions. Here the contents of accumulator are compared with the data byte by subtraction. The flags are affected, but the contents of accumulator they are not affected. Like OR and exclusive OR, this too has three variations. Those three variations are compare immediate CPI data, compare R, compare M. That is, CPI data means comparing the content of accumulator with the data byte, and the result affects the flags. Compare R, contents of accumulator are compared with the contents of one of the registers. Compare M means contents of accumulator, they are compared with the memory data whose address is indirectly pointed out by HL register pair. Now, if the content of accumulator is equal to the data byte, then the Z flag is set. And if this content is less than data, then the carry flag is set. Otherwise, the carry flag is reset. Based on this status of the flags, this instruction can help in providing jump. Now let's take an example of compare instruction. Let the content of A is E3 and the content of E is E1. On execution of compare E instruction, since the content of A is greater than the content of E, so the carry flag is not set. Based on this, it can help in providing jump instructions. Next we take on complement accumulator instruction. Now in this instruction, the contents of accumulator are complemented, and the complemented contents, they are stored back in accumulator. For example, let's say the content of A is 0001 and 1101. On execution of complement A instruction, results in A being 1110 and then 0010. Let's now take on complement carry instruction. On execution of CMC instruction, the carry bit is complemented. For example, if carry bit is 0, on execution of CMC instruction, carry bit is set. And if it is other way, that's carry bit is 1. So on execution of CMC, carry bit will be reset. Now let's discuss set carry instruction. With this instruction, the carry bit is set irrespective of its previous state. That is, if carry bit is 0, on execution of STC instruction, carry bit becomes 1. And if it is 1, that will remain 1. Now let's discuss rotate instructions. There are 4 rotate instructions: RLC, RAL, RRC, and RAR. 2 are for rotating left and 2 are for rotating right. Let us study them one by one. On execution of RLC instruction, each bit of the accumulator is shifted left. Most significant bit becomes the least significant bit, and the carry bit is modified as per MSB. Let us take an example. Let CY is 0 and A is equal to 1 0 1 1 0 1 1 1. Executing RLC instruction results in CY to be 1 and A to be 0 1 1 0 1 1 1 1. This instruction treats the accumulator and carry together as if they constitute a 9-bit register. On execution of RAL instruction, each bit of the accumulator is shifted left by 1 bit. Most significant bit of the accumulator shifts to carry, and carry bit becomes the least significant bit. Let us take an example. Let CY is 0 and A is 1 0 1 1 0 1 1 1. On executing RAL instruction, CY becomes 1 and A becomes 0 1 1 0 1 1 1 0. On execution of RRC instruction, each bit of the accumulator is shifted right by 1 bit. Least significant bit becomes most significant bit, and also least significant bit becomes carry bit. In RAR instruction, accumulator bits and carry bit are treated together as a 9-bit register. On execution of RAR instruction, each bit of this 9-bit register is shifted right by 1 bit. A0 becomes carry bit and carry bit goes to most significant bit of accumulator. Now let's study branch group of instructions. These instructions may change the program sequence. Instead of fetching the next instruction in the usual way, the microprocessor may jump or branch to another part of a program. Branch instructions are of 3 categories: jump, call, return, and restart. Jump and call can be unconditional and conditional. Restart instructions can be a software or a hardware instruction. These instructions do not affect any flag. Let us study them. When a program sequence encounters a jump instructions, the normal sequence is changed by replacing the contents of program counter with the address specified in the jump instruction. It's a 3-byte instruction. Let us see the jump instruction through a diagram. 3 bytes C3, QQ, PP of jump instruction are stored in consecutive memory locations. C3 is the opcode of jump instruction. On decoding this instruction, the new content of program counter becomes PP, QQ. Now the next instruction is fetched from memory location PP, QQ instead of PC plus 3. Let us now discuss conditional jump instructions. The sequence of a program can be altered either by the presence or absence of a condition. The conditional jump instructions are JNZ, jump if Z flag is not set, JZ, jump if Z flag is set. Likewise, JNC and JC provide jump if carry flag is not set and when it is set. Similarly, JPO and JPE provide jump if parity flag is not set and when it is set. JP and JM provides jumps if sign flag is not set and when it is set. If the specified condition is true, control is transferred to the instruction whose address is specified in the instruction itself as byte 3 and byte 2. Otherwise, control continues sequentially. Let us look at a program segment having a conditional jump instruction. At 2100 address, the program has a JC2200 instruction. On decoding this instruction, microprocessor will check the carry flag, and if it is set, then the control is shifted to 2200. Otherwise, if carry flag is reset, the control continues sequentially. Let's study a problem having both conditional and unconditional jump instructions. Here we set up a counter, then decrement it, check if the counter is 0. If no, repeat decrement counter, otherwise stop. B is used as a counter whose value is set to 3. Now, if we go through the various instructions of this program, we find that so long as Z flag is not set, JZ instruction gives a pass and the control remains in a loop, and as soon as Z flag is set, that is when B is 0, then JZ instruction provides jump to halt, and then the program comes out of loop. Call instruction is used to call a subroutine. A subroutine is a group of instructions which performs a function that occurs repeatedly in a main program. Call and return instructions are used to implement a subroutine. Call instructions can be conditional or unconditional. When a program sequence encounters the call instructions, the control is transferred unconditionally to a subroutine. After executing a subroutine, the control is transferred back to the main program with a return instruction. Let's study an example of call instruction. At 2100 address, there is a call 2200 instruction. The program branches to a subroutine stored at 2200, but before branching, it stores the next instruction, that is 2103, in a state. After executing the subroutine, the program returns back to the main program with the return instruction restoring 2103 to program counter, and then the program continues sequentially. Let us see the typical memory map. First of all, we have ROM, which has fixed instructions and data. Then we have RAM, which has the variable data, and then the stack. A stack is a memory space which is specially reserved for storing the return addresses and the data associated with other instructions like push and pop. Let us look at the stack. The stack pointer is set at 24FF. During the execution of call instruction, the 2103 address is stored in stack at 24FE and 24FD locations, and the stack pointer moves on to 24FD. During the return instruction, the stored contents 2103 is again loaded into the program counter, and stack pointer again returns to 24FF. The program sequence then continues from 2103 onwards. If the specified condition is true, the control is transferred to the subroutine. Otherwise, the control continues sequentially. The following are the conditional call instructions depending upon the status of the various flags: call no zero, call zero, call no carry, call carry, call parity odd, call parity even, call positive, and call minus. Return instructions can be unconditional or conditional. Unconditional return instruction brings back the control to the main program unconditionally, whereas conditional return brings back the control to the main program if a specified condition is satisfied. Let us look at a program incorporating a conditional call return instructions. At 2100, there is CC 2200 instruction. During execution, the microprocessor will check for the carry flag. If carry flag is set, then the control is transferred to a subroutine. Otherwise, control continues sequentially, that is from 2103 onwards. Now the return from the subroutine is also conditional. At 220F, there is an RC instruction, that is, if carry is set, then only the control is transferred to the main program, otherwise not. RSTN is a 1-byte instruction. On execution of RSTN, the program branches to 1 out of 8 fixed memory locations given by 8N. 8 RST instructions are RST0, RST1, RST2, RST3, RST4, RST5, RST6, and RST7 with their fixed memory locations specified by 8N. For example, RST6 location is 48, that is 0030 in hexadecimal. Let us look at a program segment which includes RST5 instruction. At 2509, the main program has RST5 instruction. During execution of RST5, microprocessor stores the next instruction address on the stack, and then the control is transferred to 0028 location where it finds a jump instruction. As there are only 8 memory locations reserved for RST5, so nothing much can be stored except a jump to a subroutine. After executing a subroutine, the control returns to the main program. 8085 microprocessor has a total of 74 instructions, out of which by now you must be familiar with 56 instructions. The remaining 18 instructions will be introduced to you in the next lesson.